Hey guys, in this video, we're going to talk about particles of light quantum theory. All right, and so the learning objectives of today is that we're going to look at and we're going to describe how the photoelectric effect, and we're going to talk about exactly what that is, and how it demonstrates the particle nature of light. And then we're going to also calculate the energy of light, the wavelength or frequency, if when two other variables are provided to you. Okay, so let's get to it. So what is the photoelectric effect? The photoelectric effect is when light shines on a metal surface, electrons are ejected. So here's a PhET simulation, all right, a simulation of the photoelectric effect from PhET, Colorado. But just to kind of explain what's going on here. So here we have our light source, all right, and this is our metal here, our metal surface that we're talking about. This metal surface specifically is sodium. All right. And so what's going to happen is that light is going to come from this light source. All right. It's going to hit this metal surface. And what do we expect to see is that electrons are being ejected from it. Right. And so let me kind of show you how that looks like. All right. And so I'm going to increase the intensity here. Right. And what we see here is that electrons, so we have our light being shown from our light source, and we see our electrons are being ejected. Okay. Now, a couple of things that I want to kind of talk about when it comes to this photoelectric effect. So, a couple of key points. So, the first key point we have what we call the threshold frequency. Now, the threshold frequency is the minimum frequency to which the emission of electrons to occur. That means that the light must have enough frequency for the electron to come out. And if it doesn't, all right, then we're not going to see any type of emissions of these electrons. Electrons won't be emitted. All right. And so let me kind of show you this. All right. So if you guys remembered from the previous video, is that frequency and wavelength have an inverse relationship, meaning the smaller the wavelength, the higher the frequency, and the higher the wavelength, or the longer the wavelength, the smaller the frequency. So if I increase, in this case, the wavelength, all right, now you notice what happens. No more electrons are being emitted. Even though there is light still hitting the metal, all right, it hasn't reached the threshold frequency in order for electrons to be emitted, all right? And by the looks of it here, it may seem like for sodium, electrons are emitted around 519 nanometers. So at this point, there's enough frequency within the light in order for electrons to be emitted. All right. Now, another point that I want to emphasize is that once the threshold frequency has been reached, increasing the intensity will just increase the number of electrons that are emitted. Okay. And so let me kind of show you this. All right. So let's just say, let's move this to UV spectrum and I'll lower the frequency. All right. So the frequency is by 7%. You could kind of see here the emissions of these electrons. But if I increase the intensity of the light, that means the light's brighter and brighter. All right. You start to notice that there are more electrons that are being emitted off the metal, sodium metal. So this is the photoelectron effect. So based off of the photoelectric phenomenon that we looked at earlier, all right, a scientist at Planck back in 1900s kind of looked at this and he realized there is a relationship between the frequency of the wave or the light itself and how much energy it has. And so that he came up and he found this relationship where energy is equal to Planck's constant times the frequency. All right. And based off of this equation, we could see here that both energy and frequency has a direct relationship, meaning that if the frequency increases, the energy is going to increase as well. If the energy decreases, the frequency decreases as well. All right. And so energy is always measured in joules, all right? This is Planck's constant, all right? Planck's constant is just basically that conversion factor between energy and frequency. And so it turns out to be 6.626 times 10 to the negative 4, negative 34 joule seconds. And then we have nu, which is the variable that stands for frequency, and that's in hertz or per seconds. All right, and so let's just look at examples of how we could use this equation. So let's look at this example problem. All right, what is the energy of a photon? Now, when we're talking about a photon is just a elementary packet of light. All right, so it's just basically light energy. So what is the energy of a photon with a frequency of 3.54 times 10 to the 10 to the 14th hertz? All right, so let's see what we're dealing with. So we're trying to figure out what is the energy. All right, so we're looking for E specifically, all right, but you're given the frequency, which is 3.54 times 10 to the 14th hertz. So our frequency is 3.54 times 10 to the 14th hertz. All right, and so we already know that our equation, all right, so energy is equal to Planck's constant times mu. All right. And remember, Planck's constant is 6.626 times 10 to the negative 34 joules second. All right. So if this is the case, then we know energy is equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules seconds, times the frequency, which is 3.54 times 10 to the 14th hertz. All right, hertz and seconds, I mean, they're inverses of one another, so that cancels out. And so then your answer will be in joules. So if you put this in a calculator, which I am right now, 6.626 times 10 to the negative 34 times 3.54 times 10 to the, hold on, times 10 to the 14th, then, all right, and so my energy is, right, do we have three sig figs? So it's 2.35 times 10 to the negative 19 joules. So that's our answer to this question. All right, let's look at another example. Okay, so what is the frequency of light that has the energy 1.54 times 10 to the 21st? All right, so let's see what we have here. We're looking for frequency, so we're looking for nu, all right, and the energy this time around is 1.54 times 10 to the negative 21. All right, so once again, remember our equation is E is equal to Planck's constant times nu, or times the frequency, right? And so we know that we're looking for the frequency. That's our X, right? That's what we're looking for. But this time around, we're given energy. We know energy is 1.54 times 10 to the negative 21st joules. All right. And so, and the units kind of gives away what's what if you're ever confused. Okay. But then at the same time, we know what Planck's constant is because it's a constant. All right, and so 6.626 times 10 to negative 34 joule seconds. So now I'm going to go ahead, and I'm usually one who likes to rearrange my equations first, solve for the variable that I need, and then place my numbers in there and just solve for it. And so knowing that I'm solving for nu or solving for frequency, all right, so E is equal to Planck's constant times frequency or nu. I'm gonna divide out the Planck's constant. All right, what I do to one side, do to the other. And so now we see here that frequency is equal to energy over Planck's constant. All right. And so now what I'm going to do, I'm going to plug in my numbers accordingly. So I'll plug my energy into E, obviously, and then I will plug my Planck's constant to H here. And so when we substitute our variables. So we will have 1.54 times 10 to the negative 21st joules, all right, over 6.626 times 10 to the negative 34 joules per seconds. We can see here that joules will cancel out and our last unit will be per seconds. It's exactly what we want. And then we'll just plug this into that calculator so accordingly. And so when we do this, we will get the whopping answer. And I'm typing it in as we speak. We'll get 2.32 times 10 to the 12th hertz or per seconds. So that's our answer in this case, okay? Now let's try a harder problem, all right? And so, uh, here we go. Okay, so here's our harder problem. So what is the energy of Bob's favorite color of light? And then I give you it's 454 nanometers. So let's kind of think about what's going on here, right? So it's asking you to figure out the energy of Bob's favorite color. And look at what I've given you. I gave you, and really, you want to kind of pay attention to the unit here. This is in nanometers. So this here, I actually gave you the wavelength of this color here. All right. And so that we see that the wavelength is 454 nanometers. Now, let's kind of think about what we know and what we understand. So throughout this video, we talked about that energy is equal to Planck's constant times frequency. But I didn't give you frequency, all right? I gave you the wavelength, okay? And the last video, we were able to determine the relationship between frequency and wavelength, and we noticed that c, it's the speed of light, is equal to the wavelength times the frequency. So now when you're looking at this equation here, you notice that these two are similar, or the relationship, or the variable in which these two equations share are frequency. All right. And so that means if I could figure out the frequency of this wavelength here, then I should be able to figure out what's the energy of the wavelength. And that's exactly what we're going to do. All right. So the first thing we need to do is actually convert from wavelength to frequency. All right. So that's our first step. And then we're going to go from wavelength to energy. That's the goal. That's what we're going to do. All right. And so let's go ahead and do this. Now, remember, when we're looking at units here, wavelength typically needs to be in meters. And the reason why is that the speed of light is 2.998 times 10 to the eighth meters per second. All right. And so if you notice, the biggest thing here is that the units is in meters. And so because this unit is in nanometers, we have to convert this to meters first. All right. And so let's go ahead and do that. All right, and then remember I told you guys in the last video that 1 nanometer is equal to 10 times to the negative ninth 10 to the negative ninth meters. All right, so that's the conversion. We're going from 1 nanometer to times 10 to the negative ninth meters. And so if you were to convert this straight to meters, it would simply be 454 times 10 to the negative 9 meters. All right, so that's our wavelength. Okay, and so we're going to use this equation here. All right, C equals wavelength times frequency to figure out what's our frequency. All right. And so, like I said, I like to rearrange my equations first. All right. And so we can see here that frequency is equal to speed of light over our wavelength. All right. Which is in this case 2.998 times 10 to the eighth meters per second over our wavelength is 454 times 10 to the negative 9 meters. And so we see our meters here will cross out, and all we're going to have left is per second. All right. And so we're going to put this in the calculator and then see what we get. And so when we do that effectively, 2.998 times 10 to the eighth over 454 times 10 to the negative 9, we see that our frequency in this scenario, yeah, frequency in this scenario is 6.60 times 10 to the 14 hertz. So now we have our frequency. Now that we have our frequency, all right, we could take this and plug it here to find energy. All right. And so let's go ahead and do that. And so we know that energy is equal to Planck's constant times frequency, and we know what the frequency is. So energy is equal to the Planck's constant is 6.626 times 10 to the negative 34 joules times seconds, um, times our frequency, which is 6.60 times 10 to the 14th um, hertz. All right. And so seconds and actually hertz are will cross each other out because they're just really inverses of each other. All right. And so we will plug this into the calculator. And so when we do this, we will get 6.60 times 10 to the 14. All right. When you plug this into the calculator, you get that the energy of Bob's favorite color, all right, is 4.38 times 10 to the negative 19 joules, because you were left over with joules. So this is the answer to this question.